So in this video, I'm going to talk about electromagnets, chapter 24. In a previous video, I already pretty much discussed that about the electromagnets. You saw those current carrying wire produces magnetic field. And the pattern that it produces for the straight long wire produces the concentric magnetic field around the current carrying wire. But what if you make a loop for those wire? Then each segment, small segments, makes those concentric pattern of the magnetic field, and you add up all the magnetic field that's in the circular pattern of the current carrier that has the loop. It shows that a magnetic field depends on the direction of the current. But if the direction of current like this, then inside the current carrying wire that has a loop like this, the coil is like circle, then the magnetic field will be coming into this direction or up, depends on the direction of the current. So that's pretty much it. But usually I do show some demonstration, and I can't do that here. So I found this a good video that this professor does, and I'm going to fast forward a lot of sections. If you are interested, I can send you the link so you can watch it on your own. But let's see, let me share this video. Wait, stop sharing, share with the voice.
I have a piece of plastic in which I've drilled 2 holes. I've taken a piece of dowel rod and sawed it in half, and I'm going to place it on both sides of the plastic, and use it as a form so that I can wind a coil. So I'm going to take magnet wire, thread it through the holes in a...
This is not a magnet wire, it's just a regular conductive wire.
Well, it's 25 turns. Now I will remove the dowel rod pieces from the 2 sides. So here's our 25 turn coil with the piece of plastic down the center. Now I'm going to sprinkle on some iron filings. I have sprinkled on some iron filings, and they're going to be randomly oriented. So now I'm going to apply a current to the coil, which will generate a magnetic field. And what will happen is that the iron filings will become magnetized and rotate along the magnetic field lines, so we'll be able to visualize the generated magnetic field lines. So now I'm going to turn on the current, and I might have to tap it a little bit to get the iron filings to rotate. Inside the coil, you can clearly see how the iron filings have rotated along the magnetic field lines. As you move away from the coil, you can see how those field lines start to spread out. Now, if you look at the left edge here, you can see how those magnetic field lines form closed paths around the coil. In fact, any of these magnetic field lines will form closed paths, but you can't see that for some of these because as you get farther away from the coil, the magnetic field was not strong enough to rotate the iron filings. We have...
Okay, and then what if you increase the number of turns? And so that's the electromagnets that we just saw. By having you don't need to have an actual magnet. You don't need to have an actual magnet. You could just have a wire that's looped around, and more number of turns you have, you're going to have a stronger magnetic field that's produced. And also, if you have more current, ampere running, then you're going to have a stronger magnetic field also produced, right? So instead, you don't need to have a permanent magnet. Instead of this, you could have just a loops of wire and run the current, and that acts just like this magnet. It's actually the magnetic field pattern that you saw was actually like this bar magnet. Because remember, goes like this, and you're going to see that again.
Visualize the magnetic field lines for current going around in the piece of plastic down the center of the coil.
Like this.
I have a piece of plastic that has a protective layer on each side. And the type of plastic I have is down the center of the coil.
So you can make the coil now like that. And then
generate it. This magnetic field will magnetize the iron filings, and they will rotate and align along this magnetic field. So now I'm going to apply a current, and I'm going to tap to help the filings align along the magnetic field. Inside the coil, the iron filings have all rotated to align along the length of the coil. Let me zoom in on this end. So you can see how they've aligned, and as they exit the coil, they quickly spread out and the field becomes weak and the filings outside the coil do not rotate. These magnetic field lines that are exiting the coil,
so
what
it
we
looks
found for the
something
magnetic
like this.
field generated by a coil as shown here. We found that there was a...
Okay. All right, so I'm going to show you in a whiteboard also. You already seen it in slide 2. I'll show you again. This is pretty much already covered in previous video though. Okay, so again, if we have just a one straight loop that has the current running, then a magnetic field is produced something like this. Is the direction of magnetic field, right? And then if you see the current that's coming out from the page, then the magnetic field is counterclockwise. That's the direction of magnetic field. But instead, you make a little loop that has the current running like this. Then magnetic field is produced like this, and outside into it. So if you're looking at the loop, so this is the direction. So the magnetic field is going to go into the board, and then individual them coming outside, something like this. And instead of that, now you make a number of turns. So let's see if the one that's coming out like this, then a magnetic field is produced like this. It's going to be the direction, so like this. And it has to be closed. magnetic field also line also actually never, like, it doesn't intersect like this. But anyhow, by having a number of coils like this, it produces the magnetic field like this kind of a shape. What does this magnetic field pattern though? Doesn't it look familiar to you? What if we have a bar magnet, north and south like this, bar magnet? What does the magnetic field that's generated by this bar magnet? It looks something like this, no? Uh, North and south, I wrote it wrong. North and south. Then the magnetic field is like this, out, out, out. So you don't need to have a bar magnet. Instead of a bar magnet, you could have coils turned, and that acts just like this bar magnet. So you could have just electric current to generate a magnetic field, and this is called electromagnets. Increase in current. That means increase magnetic field. Generated, and increase number of turns. You have an increase again in magnetic field. Generated. Sorry. So if you increase the current, you're going to have more. So you can control the strength of magnetic field that you want to produce by controlling the current or controlling the number of turns also. So that's the electromagnet. So right now, and this idea is used in practical situation too. You might have heard of maglev. So this is we already saw this in the previous one. And then also, if you place the iron bar in a current carrying coil, that electromagnet, because by having a coil by itself, it produces magnetic field. But if you put the unmagnetized iron in the coil, but this this iron will be magnetized, being in an external magnetic field produced by the coil. And also now the iron acts like another magnet that enforces the direction of enforces the magnetic field that's produced by the coil to make it as a stronger electromagnet. So you can put the iron bar in a current carrying coil to even make it stronger. And this idea, why do we want to do this? By generating a magnetic field, you can control the charged particle. We're going to talk about this, how we're going to talk about it in the next video. And also, you could control since that you're not using a permanent magnet, you're using current. So you can change the amount of current that's running, and you can also reverse the direction of a current to even reverse the direction of a magnetic field produced. That means that you can change the north and south. Then suddenly you have attractive magnets rather than a repulsive magnets. So you can even control that by the changing the direction. So it's a little more versatile to do. And you might have heard about maglev, that you can actually float the terrain by using this magnetic force. So you create, here I have regular, this is two permanent magnets, but let's say if I flip it, you can see that it's north and south, so it attracts. But instead of making the both side to be the unlike polarities like north and south, I could flip this to be the same north and north or south and south, and now they don't like each other. Oops, right? They don't like each other so much that it repels. So this one, the blue one, is actually floating away from the red magnet. It's floating. And use this repulsive force instead of this permanent magnet. You can have a two electro magnet or just a one electron. They use a superconductor, so they use a superconductor to have the repulsive force of the permanent magnet in it, in the train, and then you can have a superconductor or the superconductor in a train, and you could have a magnet or electromagnet underneath, and to float the train, and then you can even use the magnetic force to go forward to speed up. I have another video that I can show you about that. So here, the current carrying coil acts as an electromagnet, and how you can control the strength of electromagnet, the magnetic field produced, is by increasing the current through the coil, or increases number of turns in the coil, or adding a piece of iron inside the coil. Because that if it's a iron, unmagnetized iron, but iron is a ferromagnetic material which has magnetic domains. So that it will be induced to enforce the external magnetic field, and it's going to align along the external magnetic field to make it even stronger magnet. So this is the maglev that's was introduced, that you have a train that you float the entire train above the ground so that there's less friction. You don't have a friction from the ground anymore. You're floating, and then you can go a lot faster. 375 miles per hour. Currently, the fastest train that you can have is 220 miles per hour. So this is going to be a lot faster. And how they do is using a superconductor underneath here. So you see the picture underneath the train is the permanent magnet that's floating above the superconductor. So that when you put the permanent magnets on top of the superconductor, and this superconductor is being cooled under certain critical temperature, then it acts like a superconductor that generates the small current to repulse the permanent magnet. So it generates the magnetic field to repulse the permanent magnet above, and it's called Meissner's effect. And then that permanent magnet will be repulsed and it floats. So you use this for the maglev. Lastly, if you are interested, I can show you the video, another video. Show it once. Let's see. So here, how you see that permanent magnet is floating above the superconductor. The superconductor has been cooled by the liquid nitrogen. You see, and it can even rotate. They need to focus a little bit better. And I have another video that I can show you. So now, see, you have a block. They act like train. So this block has a superconductor inside, and then after you put the nitrogen, liquid nitrogen, to cool under a certain critical temperature, it generates, it repels. It gets repelled by the permanent magnet underneath, and it floats. And you can even go forward. Okay, so that's going to be the end of electromagnets. Next video, we're going to talk about magnetic force and moving electric charge. So, yeah. Okay, I'll see you in the next video, or I'll see you in the discussion.